we're given a real sequence an, and we're also given that 0 is no larger than am plus n, which is no larger than am plus an. In other words, we can just split up the subscripts in this inequality. And we want to show that under this condition, the sequence an over n converges. So even though we are not given the exact form of the sequence an, but it's still approachable. So this is our approach. So I'm going to fix some positive integer k, strictly positive. So if I'm given any positive integer n, I can always rewrite n into m times k plus l, where m and l are both positive integers. And also l is larger than or equal to 0 and strictly less than k. So I'm just treating l as my remainder, and k as my divisor, and n as a dividend, and m as the quotient. And of course, I'm restricting my remainder in between 0 and k, right? So now k is fixed. So next, I'm going to rewrite this sequence, an over n. Right? So let's say an over n, right, can be written into just a sub mk plus l over n, right? So now I'm going to loosen the inequality just a little bit. So my claim is that this guy is no larger than n at the bottom. And like I said, according to the given condition, we can always split up the subscript, right, while losing the inequality. So we'll split up mk and l. So I have a sub mk plus a sub l, right? So I can just loosen the inequality further. Right, so a sub mk can be written as a sub k plus all the way up to k. How many k's? Many of them, right? So again, according to our given condition, we can always loosen the inequality and while splitting up the subscript, right? So in other words, if I loosen it once, I can split up the subscript into m minus 1 many of k's and just a single k, right? And assign the subscript onto the sequence, right? Then I can keep splitting up the subscript and keep losing the inequality, until I split up all these subscript into just a single k, right? AK. How many AKs? M AKs, right? So this is easily verifiable. I have M, many of them, right? So that is M times AK plus AL, right? Then I can just split up the fraction. That is equal to, replace n, like I said, with this expression, mk plus l. I have m times ak plus. I'm going to still keep n and copy down al. Right, in that case, I can just divide both the top and bottom by just m, and that is equal to just ak over k plus l over m and plus al over n. Now, do we know the exact value of l? Don't think so, right? But for fixed n, of course, l would be fixed. But when n changes, l, of course, will also change because l is most likely dependent on the value of n, right? So in that case, just to be safe, we can make the following claim that L may or may not be a fixed number, but L is definitely bounded in between 0 and k, right? So a safe way of saying that. So which means A sub L, right, as a member of the sequence, may not be a fixed number, but it is definitely bounded, both below and above. Right, since the top is a bounded quantity and the bottom is n, what if I let n approach infinity? Right, this is right timing. So in that way, a fixed bounded quantity over some positive infinity, right? So the whole thing is going to disappear, approach 0, right? So L over m, right? L again is bounded. Does m approach infinity as n approaches infinity? Right? So maybe we can isolate m into n minus L divided by k, right? Remember, k is fixed, right? L is bounded. So in that case, when we isolate m, right, obviously as n approaches infinity, so will m, right? So again, we have a bounded quantity over some positive number that's going, positive integer that's approaching positive infinity. So this guy will also disappear. Right? It'll also approach 0. So having this in mind, we can just, while letting n approach infinity, we can take the limit supremum. Right? Not exactly limit, because I don't know if the limit exists or not. But what I do know is that the limit supremum definitely exists. Sometimes it's called limit superior or whatever. So lim sup of an over n, again, the inequality still holds, right? So that is no larger than the lim sup of this expression, right? But we already proved that the limit of this expression already exists, right? As this guy disappears and also this guy disappears. And k is fixed, right? Keep in mind. So ak over k, still a fixed number, right? So the limit of the lim sup of this expression is simply just limit, right? So what's the limit? So ak over k plus 0, just ak over k. All right, for now, k is fixed. And after we take the lim sup, right now, the left-hand side is already a fixed number, right? So could it approach positive infinity or negative infinity, or is it a finite number, right? That's the question. So my claim is that it has to be a finite number. Why? Because an, first of all, if I have a sub 1 plus 1, I have a2, right? So in that case, a2 is greater than or equal to 0. At the same time, less than or equal to a1 plus a1, twice of a1. Right, in that case, what do I have? I have twice of a1 is no smaller, right? No less than 0. In other words, a1 is bounded below. A1 is greater than or equal to 0. All right, how about A2? A2 is also bounded below. How about general an when n is greater than or equal to 3? Right, if I replace n plus n with just sub n, a sub n, n greater than or equal to 3. In that case, also greater than or equal to 0. Yeah. So all in all, no matter what n is, for any positive integer, n, a sub n is always bounded below. Right? How is it bounded above? The answer is yes. The reason is because following the same logic, we can easily verify that a sub n, first of all, can be written as a sub 1 plus 1 plus all the way up to 1. How many ones? Exactly n many ones, right? Then it's easily verifiable that this is no larger than, as we split up the subscript, right, into a sub n minus 1 plus a sub 1, right? Continue splitting it up. In the end, we can easily reach n times a1. Right? In that case, what does that mean? So which means an is no larger than n times a1. Right? If I divide both sides by n, what do I have? I have an over n is no larger than just a1. Right? a1 is already a fixed number, in which case an over n is a sequence, is bounded above. Right? So we've proven that an is bound. So in which case this implies that an over n, right? Divide both sides by n is also bounded below, right? Same time bounded above. Right? So the sequence an over n is both bounded below and above. So therefore the sequence is bounded. So there's no way for lim sup to approach positive infinity or a negative infinity, right? This has to be a finite constant. So some finite constant is no larger than ak over k, where k is a fixed positive integer, right? So having this in mind, how about we let k approach infinity? Right? Does the inequality still hold? Right? This time we'll let k approach infinity. Right? Like I said, when I fixed k, was there any restrictions? No. Right? It says I can fix any positive integer k. Right? I can always represent n into the following expressions. Right? So this inequality always holds for any fixed positive integer k, right? So which means if I let k approach infinity, right, and take lim inf on both sides, this inequality should still hold true, right? Some finite constant should still be less than or equal to the lim inf, right? I cannot take the limit yet, but I can take the lim inf, right? Because lim inf definitely exists. So in other words, lim sup as n approaches infinity of an over n is still no larger than lim inf as k approaches infinity of ak over k. Right? The same concept, just different notation, right? We can treat it as if n approaches infinity of an over n, right? Still the same thing. So lim sup is no larger than lim inf, and at the same time we know for a fact that lim inf is no larger than lim sup as well. So the only possible explanation is that lim sup has to equal to lim inf, which means the limit has to exist, right? Of an over n, the limit has to exist, right? So is it a finite number, or is it approaching positive infinity or negative infinity? I say it has to be a finite number. It cannot approach to positive or negative infinity if we generalize the limits. The reason is because we've already shown that the sequence is bounded both below and above. Right? At the same time, we've also shown that the limit of the sequence really exists. So therefore, it has to be a finite number.